This is a demonstration of the Architecture Framework for Fault Management Assessment and Design, or AFMAD, toolset. The AFMAD toolset consists of a number of tools that can be used to generate and do analysis on AADL models. Some of the tools we will be demonstrating include automatic component generation, which takes in a spreadsheet and generates component model library. Design Space Explorer, which allows us to select subset architectures from that library and create individual model instances. Trade Space Explorer then runs analysis tools on each of the instances. These tools can be built-in OSATE analysis tools or some of the tools developed under the AFMAD program. The results of all of this analysis are put into the trade study database, and this database is then brought into a tool from Penn State called Trade Space Visualizer, which allows us to visualize and explore the trade space. For this demonstration, we're going to be using an example model of a CubeSat. The CubeSat consists of three main systems. We have a support mechanical system, a mission payload system, and a support electronic system. Now, for the examples that we'll be looking at today, we're going to look at trade-offs of different solar panel power generation options. So we'll be looking in more detail at the support electronics system. The support electronics system includes a number of subcomponents, including a control software, attitude control system, power system, telemetry, and the control board. Since we're looking at power generation, we'll look more closely into the power system. The power system consists of three main types of components. We'll have an EPS, a battery, and one or more solar panels. And what we'll be doing is looking at different options for solar panels and their configurations and looking at the trade-offs. Moving into the OSATE environment, we'll go and look at the top level of our CubeSat model. Here's what our CubeSat model looks like in AADL, and as you can see, we have three different subcomponents or subsystems, including the support mechanical, the support electronics, and the mission payload. And each of these systems is modeled down to detailed level until we get down to individual components. And these components are components that are available from different vendors. This is an example of the file that's the input for automatic component generation. This file consists of rows for each of the individual components and columns for each of the properties that will be modeled for a component. So for example, we have a column for the type of device it is, a column for a unique implementation or a unique name for the device. We have columns for input data ports, output data ports, a listing of any flows that this device might be part of, a column for input power connections and output power connections for any devices that may be power generators. Our CubeSat model also includes a three-state error model. The errors consist of either an operational state, a permanent failure state, or a transient failure state. And this column lists out each of those states and probabilities for each of those states for each component. Other columns in this file include power budget and power supply as used by some of the analysis tools. Weight is used by the weight analysis tool, and latency. We also include a number of other more custom parameters just to describe these components for future analysis tools. Now this entire file is input into our automatic component generation, and the output of component generation is a parts database. So here's what the parts database looks like, and so for an example component, we list out the unique component name. We have properties for the power budgets, the weights, the latency, and then all of the other properties are just listed as custom properties. The error behavior probabilities are put in here as well. Now this particular database is the components that will be used by all of the other portions of the model. So we're going to close this database. We're going to go back to our top level model, and we're going to select out and create a particular implementation. And to do this, we're going to be using our Design Space Explorer tool. So we're going to select Design Space Explorer, and then we will pull up the Design Space Explorer window. I'm going to increase the size a little bit so that we can take a closer look at this model. So now we're at the very top level of the CubeSat model, and these little yellow icons tell us that there are a number of selections yet to be made on the model. So let's open up the model and see that we have our three different subsystems: the mechanical, the electronics, and the payload. And each of these subsystems can be opened further to get multiple options. Now, one of the features that we put into Design Space Explorer is the concept of a stub. And what a stub is it's essentially a generic implementation for that subsystem or even that subcomponent. And the purpose of a stub is to allow us to focus in on individual components without having to go into that level of detail for other components. So for example, for today's analysis, we're really interested in solar panel generation, and so we really don't want to have to go all the way down the mechanical tree and pick out structure components and things. So what we can do is just select the mechanical stub, and that'll essentially give us generic properties for that entire subsystem. I want to do the exact same thing for the payload and select a payload stub. But for the support electronics, we're actually going to be doing some trade-offs here. So we're going to select support electronics implementation, and now we have the subsystems. And for telemetry, we're going to select a sub. For attitude control, we'll select a stub, and for the control board, we'll select a stub. But now for the power system, we're actually going to define a specific instance. And for this particular example, I want to pick a static solar panel. And now I need to go in and select a battery. And at this point, we are way down at the component level. We are now making selections from within our parts database. So I'll select a specific battery. The same thing for a solar panel. I'll select a specific solar panel, and I will select an EPS. So now note that all of the yellow warning symbols have gone away, which means we have made all of the selections to define a unique instance. I'm going to shrink this window down again. Now within OSATE, now we're going to generate an instance so that we can run our analysis tools. And we use this icon here, and what that does is that generates a unique instance that we can now use in other analysis tools. I do want to point out that we have other ways of generating these instances. If we had left a couple of these decisions unchecked, such that there were multiple options, we could actually ask DSE, by using this particular icon, to generate a subset of all of the possible configurations. Now with our big CubeSat model, we need to be careful because this space can get very, very large. For this example, we're just going to use one instance. So taking a look at our instance we just generated, there are a number of analysis tools that we can run on this. We could certainly use any of the built-in analysis tools. For example, we could do the weight analysis or the power analysis. But what I want to show you is a tool we developed under the AFMAD program for the RBD, or the Reliability Block Diagram Analysis. And what RBD does is it looks at the error states and goes through and adds up, computes the probabilities for the entire system for each of the error states by going all the way down through the model, looking at the probabilities for each of the components. Now there is a built-in RBD tool built into OSATE, and what that tool does is it runs this analysis for a single error state. you manually enter which error state you want to run the analysis for, and it gives you back the probability. We customized that tool under AFMAD to give us a report for all of the error states within the model, so you can see that we have both the failed transient and the failed permanent. In addition, we customized this report to generate a CSV file, and here it is under Reports RBD. And essentially this CSV file gives us the same information, but now it's in a file that we could parse and use in our automated analysis. And we'll show you how we use that in just a moment. I will point out that we also have a version of RBD report that doesn't generate any display, and we use that for our automated analysis or our batch analysis. Now we could go through and by hand or manually run all of these analysis tools, but within AFMAD we've developed a shortcut. So if we select the instance and we select the compile analysis results, what this does is this runs the power analysis tool and generates the power report. It runs the latency analysis tool, and it runs the RBD analysis and the weight analysis. And then it puts all of those results into a compiled file, a CSV file once again, and I'll show you the format for this file. Essentially has a row for each instance and a column for the results of each of the analysis tools. So for example, we have a capacity, supply, and budget from the power analysis tool, and we have the total mass from the mass analysis tool, and the probabilities from each of the RBD analysis tools, and then latencies for all of the flows that were defined. Now what we want to do is we want to take that analysis result and we want to start building up our trade space. And the way we're going to do that is we're going to create another file called a collection file. And we have an option here to essentially add the results of this analysis to the collection file. And so that will now create a collection file here that's compiling the results every time we do an analysis. So now what we would do is we would go back to Design Space Explorer and go through and create another instance. So this time I'm going to go in and I'm going to select a different kind of solar panel, and we'll select a different battery option here. And we will go back, and now we're going to generate another instance. And so we've got a second instance generated now, and we will run our analysis. Run all of our analysis tools on that instance. And we will add all of those results to our collection file. So then we can go look at our collection file now. We'll pull that over. Now our collection file has two different rows, one for each instance, and the results of all of the analysis done on each of those instances. And we could go in and run this analysis on multiple instances using Design Space Explorer. What I want to show you now is how we can look at the results, how we can visualize the results for this collection file. And the way we do that is we use a program out of Penn State called Trade Space Visualizer. So here's the output of Trade Space Visualizer on one of our collection files. I'll shrink this up so we can view it a little bit better. And what we have is we've selected a number of the property values in our collection file for axis on the 3D plot. And if I move this around, you can see the different points, the different instances are plotted in this three-dimensional space that includes power supplied, power budgeted, and the mass. Now, this particular trade study was run looking at a number of solar panel configuration options, including static solar panels and also some deployed solar panels. Now, if we pick one of these points, say one way up here, and we select that point, we can get a report of the properties essentially that generated that point. So we can see the capacity and we can see the unique instance number. And this one happens to be a deployed solar panel, and we can tell because it uses quite a bit of power. In addition to power it generates, it actually uses power, and so it's way up there on the power budget curve. Other options down in here that don't use much power and have less mass are some of the static options. But you can see how we could use this tool to explore the trade space that's generated by the Trade Space Explorer system. Now let's show you one other feature of Trade Space Explorer. The input to Trade Space Explorer in this case is the model, and what we will do is generate a list of properties, all of the possible properties that could be manipulated. This is the input to our Architecture Model Experiment Orchestrator, another tool developed, which allows us to select property values for specific properties and generate test cases. These test cases are then used by Trade Space Explorer, which generates an instance for each test case, runs all of the analysis tools, and then populates our trade space or our compiled result file. The way we like to think of our trade space file is just a giant matrix, and think of each of the rows as an instance. Now, these instances could be architectural variants coming from Design Space Explorer, or they could be property variations generated by Trade Space Explorer. Columns within this trade space include a unique identifier of the instance, or the signature, and the different property values that were manipulated by Trade Space Explorer. Other columns are the results of any of the analysis tools that were run. Essentially, each analysis tool adds one or more columns. Now, it's also possible for other tools outside of OSATE and outside of AFMAD to generate other analysis results. They could use property values to generate other results, and these columns could just be added to the trade space. Let me show you an example of how this would work. So we will select one of the instances that we generated earlier with Design Space Explorer, and now we will use the AFMAD tool List Properties to generate a report of all of the properties for that particular instance. Let me show you what this property file looks like. It's a CSV file, and it has a row for each of the different properties and a column listing out the component, the feature, the specific property name, and then the current property value within the model. We also include kind of a min and a max and a default step size that's used by the user interface. Now, this property file is used as input into the next tool called AMIO. And let me show you how AMIO works. So AMIO provides a nice user interface where we can select individual properties. In this pane, I have a list of the different components available in this particular instance, and so I'm going to select a solar panel. I'm going to select one property, the power out and the power supplied, and it now gives me a window with the current default value in the model, but I can now specify a minimum and a maximum to run a test over this property, and also a step size. And for this particular example, I'm going to make the step size a little bit bigger so we don't generate too many instances. Now I'm going to select another component. Let's select the battery and the power supplied by the battery, and we get a similar window here. And let me select a step size there. So now I've selected a couple of different component properties and ranges of values that I want to run tests over. Now we can either generate all possible combinations of those property values, or as the state space gets larger, we might want to constrain that a little bit, so we have the option to generate pairwise combinations. We also have an option to generate random iterations. If you select this option, you essentially need to tell it how many iterations you want to generate, or how many test cases you want to generate. For our example here, we'll go with pairwise, and we will generate those values. Save them off to our file. So let's look at the output of this file now. It generates another CSV file. And in this particular example, we generated 12 different test cases. And what this test file includes is essentially a line for each property value in its setting. And so for test 1, set solar panel to this value, set the battery to this value. For test 2, set the solar panel here. And this is the way we define all of our test cases. This file is now the input for TradeSpace Explorer. So we will now go up to AFMAD and select TradeSpace Explorer. And what the TradeSpace Explorer tool is now doing is setting those property values for each instance, generating a sample of that instance, and then running all of the analysis tools on that instance, and putting the analysis result into our collection file. Now we'll show the output of the TradeSpace Explorer. We'll go up here and open up our collection file. And the collection file has now had 12 more tests added, so now we have a number of different instances, and each of them had different configurations for supply and budget, and all the results of all of the analysis tools are populated. Now if we look at that file with TradeSpace Visualizer, what we've done here is brought in a collection file that we did earlier, looking at a number of different trade-offs for different types of solar panel configurations. And on this axis we're plotting the supply, on this axis the budget, and on this axis the failed permanent. And we've enabled another option within TSV is to color the points. In this particular setting, we're coloring them within the based on the budget, and so red points are not going to be using as much power as some of the blue points. And as you can see, there's a nice separation between our deployed solar panels and our static solar panels, especially based on failure rates. Deployed solar panels have much higher failures, and we can kind of see the spread as far as what they could generate as far as supply, that was one of the parameters that we varied with TSE. We hope you found this demonstration useful. For more information on AFMAD and other programs, please visit www.adventiumlabs.com.